Welcome to part 2 in our discussion of covariance and correlation. Here's a data set of body fat percentage and weight. So this is a data set of individuals. And our question is body fat percentage related to your weight? So we're not looking at US states. Each data point here is a particular individual. And we're letting X equal to a person's body fat percentage and Y equal to a person's weight. So first off, just looking at the scatter plot, the pattern of data, we can see that there's some kind of suggestive positive linear relationship, meaning as a person's body fat percentage increases, we'd expect their weight to increase in general. And as a body fat percentage of a person decreases, we'd expect their weight to decrease, meaning these two variables tend to move together, and we call that a positive linear relationship. So far, we've talked about a measure of association called covariance. So let's calculate covariance. The covariance between these two variables is about 140.802. You can see that the covariance is just based on reorienting each data point in reference to the mean of X and the mean of Y. And so from that, we can calculate the covariance, which is simply a measure of the average of the cross products between X and Y. Substantively, you can look at the scatter plot, and by dividing the scatter plot into these four quadrants with respect to the mean of X and mean of Y, we can see that in general, we have more data points in those quadrants that have positive cross products. So the upper right-hand quadrant consists of those values that are above the mean of Y and above the mean of X. And so you multiply those deviations together and you get positive values. In the lower left-hand quadrant, you have data points that in general are below the mean of X and below the mean of Y. And so those data points have two negative deviations, but when we multiply those, we get positive cross products. And so that positive linear relationship is a function of the fact that we have more data points in the upper right, and in the lower left. And so when we calculate covariance, we get this positive measure. However, there's a problem with covariance. Covariance can only give us the size, the sign rather, or the direction. It cannot give us the size or the strength. So covariance, we know it's positive, negative, or zero. But in terms of the overall strength or magnitude, or the size, we don't know, because covariance, it's dependent on the units. All we know with a covariance of 140.802 is that weight is positively associated with body fat percentage. Right? But we want perhaps a measure of strength. Is this a moderate relationship, a weak relationship? Well, the solution is to standardize covariance. We call a standardized version of the covariance correlation. So here's the formula for a correlation with a sample of data. All we're doing is we're standardizing the sample covariance. You take the sample covariance of X and Y, and you divide by the sample standard deviation of X times the sample standard deviation of Y. And then we get this value of the correlation, which we call R when we have a sample. Intuitively, keep in mind that the sample covariance is expressed in units of X and Y, the standard deviation is expressed in units of X, and the sample standard deviation is expressed in units of Y. Well, those units cancel each other out, and so that the correlation ends up being unitless. This is an important property of correlation. Let's look at the formula for correlation for a population. It's the same, right? The only difference is that we use Greek letters because we like to keep track of whether we're calculating from a population or not. But the overall idea is the same, in the sense you take a population covariance and you divide by the population standard deviation of X times the population standard deviation of Y. And the result is a covariance of a population, a correlation of a population rather, that we call rho. Okay, that's all that Greek letter refers to. The correlation coefficient has some nice properties. First of all, it gives us not only the direction or sign of a pattern between two variables of a linear relationship, but it also gives us the strength or magnitude. Correlations, because they are unitless, because those units in the numerator and denominator cancel each other out, correlations are bounded between -1 and +1 as a result of dividing by these standard deviations. It's a very useful measure, and it keeps the sign from covariance, but it also gives us the strength of the relationship. You just take the absolute value of the value for the correlation, and we have an idea of the strength. So negative 0.8, it's stronger than 0.4 because the absolute value of negative 0.8 is greater than that for 0.4. So we can take a data set, use covariance and the standard deviation x and standard deviation of y to calculate correlation. So here we have body fat percentage. The standard deviation for body fat percentage is 8. The standard deviation for weight in pounds is about 29.5. And earlier we mentioned that the covariance is 140.80. So you divide the covariance by the product of these two standard deviations. The units of body fat percentage and weight in pounds will cancel out. And then by dividing by the standard deviations, we're going to have this bounding between -1 and +1 inclusive for correlation. So the result of these calculations is a correlation coefficient of 0.596. Again, all we're doing is we're taking the covariance, standardizing it by dividing by the product of these two standard deviations. Question is, how can we interpret this? We know that 0.596 has a greater magnitude than 0.4 and a smaller magnitude than 0.9, but substantively, what does a correlation coefficient of 0.596 mean? Well, there are a few rules of thumb. This is a rule of thumb for interpreting correlation magnitude. It will vary from discipline to discipline. So if you talk to a psychologist, they might have a different set of criteria for understanding the magnitude of correlation than a sociologist or an economist. But this is just a general set of guidelines. The closer you are to 0 in terms of the magnitude of the correlation, the weaker the linear relationship. The closer the magnitude is to 1, the stronger the relationship. So in general, we can say a very weak relationship is when the correlation has a magnitude of 0 to 0.2. If it's between 0.2 and 0.4, it's weak or moderate. 0.4 to 0.6, it's medium to substantial. 0.6 to 0.8 is very strong. 0.8 to 1 is extremely strong. Correlations in practice close to 1 are really quite rare. Let's look at a few examples from our data set. So in this data set of individuals, we can calculate different scatter plots and different correlation coefficients. So here's a correlation between body fat percentage and a person's height. It's 0.032. Using this set of guidelines, this is a very weak magnitude, but it is a positive direction. This is also reflected in the scatter plot. The scatter plot looks like a cloud. Okay? It's basically just a bunch of noise. Right? You can't even really tell that there's a positive, very, very small positive relationship between these two. If we calculate the correlation between body fat percentage and age, we get a value of 0.256. So using our guidelines, that's a weak to moderate magnitude, and it's a positive direction. You can see in the scatter plot, there's some vague semblance. You can see some pattern in the data that as body fat percentage increases, there tends to be a slight increase in age. So they do move together in a very slight, weak way. But the point is, there's some correspondence between the correlation coefficient and the scatter plot. If we look at body fat percentage and weight, what we've been looking at so far, we get this correlation coefficient of 0.596. This is a medium to substantial magnitude, and it's a positive direction. And you can see that in this data set. So you see the movement from the lower left to the upper right, suggesting a positive linear relationship, and there's some sort of clustering. Okay? There's some sort of pattern in the data. If we calculate the correlation coefficient between body fat percentage and sort of the size of one's chest in circumference, we get this value of 0.682. So this is a positive direction, and using the guidelines that we've just discussed, it's a very strong magnitude. And you can see, compared to the previous scatter plot, you can see that there is a more obvious pattern in the data. You can see sort of a greater clustering around some set of, some set of data from the lower left to the upper right. You can see this sort of pattern. If we look at the correlation between body fat percentage and abdomen, we get this value of 0.812. This is an extremely strong magnitude, and it's a positive direction. And you can see that it's as we get closer to 1, you see a stronger pattern in the scatter plot of data. But of course, direction matters too. We've looked at positive linear relationships so far, but here's a negative relationship. So if we look at the correlation of age and height, we get this correlation coefficient of negative 0.27. And you can see that in the scatter plot. The pattern seems to go from the upper left-hand corner to the lower right-hand corner. And this is a weak to moderate magnitude. So in sum, we can think about correlation as giving us a measure of association that is unitless, that tells us both sign and size. To put another way, we know the direction of the relationship, whether it's negative, positive, or 0, and we know the magnitude, the strength of the relationship. And you will see correlation time and time again. It's probably one of the most frequently used measures of association. And with that, we will conclude our discussion of correlation and understanding what it really consists of.